Okay, hello people. Today, as I promised you last time, we will see the final part of chapter 13, flow overcomes some aspects, and then we will start chapter 14 devoted to hypersonic flow. 2 chapters in one day, let's say. At least we will try to do it. Flow over cones is different from flow over wedges, which we already studied before. The difference is that flow over cone is three-dimensional, and the area, cross-sectional area of flow changes in a different way that it changes for b-dimensional body. For example, if I have b-dimensional body of similar shape, which you can see on figure 16, we would have some object, right? And the third dimension, like this. Okay, the z component is constant, is not changing. Okay, is not changing. In three-dimensional space, we have axisymmetric rotational body. Here, in case of b-dimensional case, we can calculate area of flow, cross-sectional area of flow, as A would be equal to a distance, to a size, delta y multiplied by the coordinate. Right? If we have this delta y is okay, probably would be nice to remove this third dimension and denote in any specific cross section, any arbitrary cross section, delta y as this distance inside flow, inside the air. So for b-dimensional case, it's linear, is a product of two linear dimensions, two independent dimensions. And in case of rotational bodies, if we have r components, r coordinate, we are calculating like this. Okay, delta r, and here would be okay, how much? Okay, total is r coordinate. We would calculate this as r in square minus. No, probably better. No, sorry. Delta r in square multiplied by pi. So this is the area in axisymmetric body, area of flow, where we have second order or linear dimension in square. In case of two-dimensional flow, we have a linear dimension in just first order. Since the area changes differently in first or second order for different types of flow, it will result in two different models, two very different models and two different flow behaviors. Also in figure 16, we can see perspective on axisymmetric body showing us from perspective point of view flow around axisymmetric body. There is a specific boundary conditions that we take into account for such flow is shown on the left top corner of screen, showing that any parameter will not change with respect to angle phi. So flow property stay constant along this circular line at any point in space, and constant radius, but with changing phi angle. So we can reduce our task from three-dimensional to b-dimensional task, since we know that in axisymmetric flow, phi is or phi angle does not influence on flow properties. Here on figure 17, we have supersonic flow over cone schematic, and this figure shows that an approach which we use to calculate flow over combs. This approach says us that flow properties and thermodynamic properties and velocity are constant along a ray. This ray is a straight line from the leading edge of the body, in this case is a conical shaped body, and this ray has an angle theta. So theta is the only parameter which is changing from one ray to another, and all flow properties would be functions of this ray. Pressure, temperature, density, and velocity are constant along a ray. This is the assumption which we have to take into account to build our flow model. With this assumption, we can transform flow equations, our original continuity, momentum, and energy equations, and conclude in the following equations. How this transformation is made, you can see from the book. I'm not sure this is important to show you all these transformations, since, as you will find very soon, we cannot calculate directly by this model. Equation 80 is representing to us change of velocity with respect to angle theta, arbitrary angle theta. This angle theta is changing from theta c on the wall of the surface, is the angle describes the surface, and theta s, which is the angle of shock wave. These two angles, theta s and theta c, are limiting angles where flow parameters change. Outside of these angles, we have no flow, or we have flow constant and uniform. For example, inside the body, we know that flow doesn't happen, and outside of shock wave at m infinite, we have all flow properties. Okay, I will include also velocity here, constant. All flow properties constant, as we might observe from experiment, as we might see from CFD analysis. Outside of shockwave, there is no sense to calculate, because all flow properties stays constant and equal to undisturbed infinite conditions. Can be defined by Mach number and flight altitude, for example. So only in this region between theta c and theta s flow changes, and it's changing according to theta angle, which varies from theta c to theta s. Equation 80 is a combination of flow equations. As a result, this equation, as you can see, is a differential equation, ordinary differential equation of just one parameter, which is velocity. Here we see that velocity changes from with respect to this theta, right? And the solution of such equation could be obtained, for example, by method Runge-Kutta, which allows to integrate this equation and obtain such solution. Method Runge-Kutta, iterative process of calculation. To calculate this equation, we must define boundary conditions. Force boundary conditions is given on the shock wave. After the shock wave, we can use oblique shock wave relations to obtain flow properties after shock wave, and not the angle of shock wave, because angle of shock wave we do not know initially, but we can guess some initial value. So theta s is our first guess, our first iteration. We start with some theta s, which is bigger than theta c. There is, as we can see from theory of hypersonic flow, we will see very soon that there is a relation between theta s and theta c for hypersonic flow. So we can use some similar relation for supersonic flow, and we can guess what would be a good value for initial parameter of theta s. On this shock wave, we assume boundary condition velocity, calculated by oblique shock wave theory. And we know that another boundary condition is on the surface of cone, which is saying to us that all velocity is moving according to shape or according to angle of body. On the surface, only tangential component of velocity will appear, and angular tangential component will appear, and the normal component of velocity will not happen. So this is the second boundary condition we have. Since the equation 80 is a second order equation, we must have these two boundary conditions. One boundary condition after shock wave, and second boundary condition on the surface of a conical body. And then integrating this equation, we obtain the solution. Not always we cannot get this solution from the first attempt, because our guess of theta s would be wrong, so solution will not converge in will not coincide with the parameters on the surface once we start to integrate this equation. And if it does not converge quite precisely, we can calculate again. We change theta s according to our estimation. We change angle theta s until the moment when solution of equation 80 converges on the surface of cone and flow is exactly parallel to the conical surface. So this is iterative process. This iterative process Anderson explains in the book in chapter 13.9, and let me see if it's here. It consists of 5 steps. 5 steps. This is section 13.6.3. 5 steps how to take initial value of angle of shock wave, and how to provide integration of equations, and how to check if solution satisfies physical process. I mean, physical process means that velocity coincides with the direction of body. As a consequence of this model, we can find also equation 81, which gives us a relation between arbitrary velocity at any arbitrary point, maximum velocity in the flow, and it's so-called dimensionless velocity, dimension v asterisk, or v prime, sorry, v prime. Equation 81 is a function of Mach number, since flow after shock wave is asentropic. We can use all asentropic relations, which we studied, I think, on chapter 8 and used on chapter 9 and 10 to obtain some flow properties inside asentropic regions. So before shock wave, all flow properties are constant, and flow, of course, is also asentropic. After shock wave, flow is also asentropic, and just on the shock wave, flow is non-isentropic, just on the shock wave transition. In all other regions, flow is isentropic, and we can use isentropic functions to obtain flow properties, thermodynamic mostly properties, as functions of Mach number. So we calculate velocity behavior, we calculate Mach number with equation 81 corresponding to velocities we obtain, and we calculate all other thermodynamic properties: density, pressure, and temperature. This is briefly, I explain you how to calculate axisymmetric flow. You see that there is no analytical model, or algebraic analytical model. There is analytical model based on ordinary differential equation. allowing to provide this calculation. As you see that since there is no simple solution, we cannot have a database, right? And this solution must be obtained every time you approach to solve this problem. This is actually one reason why in work 1 you calculate b-dimensional flow instead of axisymmetric flow, because calculation of axisymmetric flow is way more difficult than simple planar b-dimensional flow. Next slide shows to us change of the angle of shock wave with respect to angle of cone. You see that from 0 to 60 degrees approximately this variation of angle of body happens, and it shows to us that angle of shock wave can be obtained as function of Mach number, shown for 3 different Mach numbers: Mach 1.5, Mach 2, and Mach 5. For each of these Mach numbers, we have limiting or maximum possible c or c theta. Let me try to make straight line. Yeah, that corresponds to some value of the angle of the body, saying to us the maximum angle at which oblique shock wave may exist. In figure 21, we see two cases. Theta c less than this maximum, so we have attached shock wave on the cone, and when angle is bigger than theta c maximum, shock wave is detached and turns bow shock wave. Bigger is Mach number, bigger is this angle of body. We see that already for Mach 5 we can have, we can have very big value of body. I think something close to 54 degrees. Maximum possible angle of body. For small Mach number, of course, this angle could be small, maximum 30 degrees for Mach 1.5. This is about the existence of attached shock wave and detached, not about efficiency. Of course, we remember that bigger is the angle of body, bigger is the loss, or bigger are the losses on this shock wave. And for hypersonic flow, losses can be significant, very high. We can lose almost all energy on this shock wave, as you remember. Losses on shock wave for b-dimensional flow and for axisymmetric flow can be calculated using same relations on shock wave because they involve not geometry, but they involve transition and thermodynamic properties, laws of thermodynamics, which work for b-dimensional as well as for three-dimensional case. So these losses can be estimated by using previously studied equations. Here, this picture is also showing to us a comparison between wedge and cone. Wedge is a two-dimensional structure which we calculate in work 1, and cone is three-dimensional structure which you can see on figure 23. We see that for wedge, maximum theta angle is smaller than for cone. For same Mach number, it's Mach 2 in this case. And this happens because area is changing proportional to linear dimension, and for conical shape, area changes proportional to square of linear dimension. So since area increases faster for three-dimensional body, maximum conical angle or angle of cone could be bigger, okay, to achieve same values of area, occupied area, let's say. Okay. that's the end of part 13. Please let me know if you have questions on this topic. I can wait some short time before I prepare presentation for chapter 14. Let me know if you have questions, please. Okay, I see no questions, so I think we can start Hypersonic Flow chapter 14 from the book, devoted to flow at a very high Mach number. Hypersonic flow starts from approximately Mach 5. There is no exact definition, but usually people use Mach 5 as the limiting factor between supersonic and hypersonic flow. There are two aspects which Anderson presents in this chapter. They are qualitative aspects where we discuss flow structure, and quantitative aspects where we discuss the values and models of flow. Here to motivate study of, there is one intersection of figures. It should be different. To motivate study of hypersonic flow shows quite interesting structure of X-43 flight vehicle that is designed by NASA to fly with hypersonic velocity. Hypersonic velocity where Mach number is high, Mach more than 5, or okay, let's use this more or equal than 5, is characterized by extremely high temperature on the surface because friction and because shock waves create elevated temperature. Transformation of kinetic energy to thermal energy happens mostly on the surface of these flight vehicles. As you will see, shock waves are very close to a body, which cause additional and mixing in this region between shock wave and wall, and causes very, very high temperatures. Which could be these temperatures? They can start from relatively small, several hundreds of centigrade, and can reach really high values, some thousands of centigrades. The values we will see a bit later. To protect any flight vehicles flying at hypersonic velocity, we must use advanced materials to cover its surface, especially to cover most heated surfaces such as nose and wings, all surfaces which meet first this flow, where flow tries to be moved or near stagnation points. Here on figure 2, we have some surfaces covered by carbon-carbon. The most responsible carbon-carbon is a composite carbon with very good thermal properties. Material made only of carbon with the different with the special structure which is also quite resistant to mechanical loads. What is carbon-carbon and how it is produced, you can see on other courses of materials. For us, it's important that this composite material has quite significant thermal resistance. Carbon by itself has temperature of destruction near 3800, and it's an ablative material, so it does not liquefy. It turns from solid to gaseous state. Very nice resistant material. Then also there are other alloys used, which you can see here, for example, tungsten or Haynes alloy, which have specific properties for not just thermal resistance, but also for elongated bodies. They must have some mechanical properties that will resist on formation of cracks, resistant to vibrations, and other properties. Usually, thermal resistant materials are quite fragile. So the aerodynamic body cannot be built from one single piece. If you see, for example, space shuttle, which is covered by plates of carbon and plates of ceramic, is made of pieces which have their integrity during heating. So internal loads of that appear on the body due to thermal expansion are quite high, and materials used in such structures should be resistant to these internal thermal loads, which cause also mechanical loads inside material. So this is why all components pieces of different pieces. By the way, is not just typical for hypersonic applications, but also for some fast airplanes, supersonic airplanes that fly with the Mach close to Mach 2.5, Mach 3. That airplanes are built intentionally with gaps in their fuel tank, for example, and during flight, due to thermal heating of structure, these gaps inside the tank disappear and leakage of propellant stops. And this is intentionally made to compensate expansion and thermal expansion and possible destruction of structure. Here is same. If you look to space shuttle, there are many photos, or you can personally see it when you have such an opportunity. You will see that there are gaps between these elements intentionally made to compensate thermal expansion of structure. It's quite important to remember this aspect. I'm not saying that it's very expensive, and also this is hard from technological point of view. These aspects we also need to consider. This is why very few countries have technology to fly with hypersonic velocity. Hypersonic flight vehicles are advanced vehicles allowing us to fly very fast, but also companies which design such vehicles must solve many technical problems and invest a huge amount of money on this development. Now I would like to show you on figure 14.3 structure of flow with hypersonic flow, structure flow with hypersonic conditions, where Mach infinite is 36. We can see that a body of 15 degrees also generated shock wave of angle 18 degrees. So angle of shock wave is very close to angle of the body, to only 3 degrees. Inside this 3 degrees gap, we have flow transforming from supersonic, high supersonic or hypersonic velocity to zero flow velocity on the wall. Okay, such a huge transformation, such a huge gradient of velocity does not leave space for smooth flow transition. Flow is quite rapidly changing, and practically all space between shock wave and the body is occupied by a boundary layer. This is so-called shock layer. Shock layer is a combination between a boundary layer and shock wave. So shock wave is constantly attached to this boundary layer. So, or we can say differently that shock layer is a combination of shock wave or combination of boundary layer with shock wave. Huge transformations happen on this shock layer. Flow velocity changes from very high to practically zero, and on this layer, most part of energy is transformed to thermal energy. We can also see two cases which Anderson proposes to us on figure 4. Is the viscous interaction of flat plate at hypersonic speeds, where we take into account viscous interaction or do not take into account this presence of shock wave. And there are two different types of models. Depending on which model we are using, we will see two different flow structure, two different behavior of thermodynamic properties. In case A, where there is no viscous interaction, we see that there is a Mach angle appears, or Mach wave appears. Mach wave corresponds to Mach angle mu, which we studied before. We know that Mach wave would have, or Mach angle would have very small value because Mach number is extremely high. And in such case, idealized picture, we see that pressure will be constant along the plate. Why plate? Because using this concept of plate, it is easier to build any analytical or simple numerical model. So this is why we have plate instead of any body with a complex or let's say a curved shape. In case B of viscous interaction, where we see presence of shock wave, we have change of pressure, as you can see on figure B. It has its maximum on the tip of the plate, because on this tip we have a stagnation point because boundary layer by itself creates obstacle for flow. So inside this front point of flow, which are marked by blue, we see zero velocity. At this point, pressure would be close to stagnation pressure. This point is small, but this rise of pressure will always exist. Okay. Because of presence of boundary layer with some thickness. Okay. Boundary layer is the reason why elevation of pressure at the leading edge happens. And then when boundary layer becomes more or less stabilized, it becomes more constant, let's say. Thickness increases, but not so much with respect to initial change of its thickness. Then pressure stabilizes as well and starts to be higher but close to infinite pressure, as you can see on figure B, upper part of figure B. Behavior A and behavior B can be seen on analytical and numerical approach. Of course, in real life, we will only have viscous interaction, because in real life, boundary layer will be always present. But it's always our choice if we calculate or not boundary layer analytically or numerically. In case of absence of boundary layer, we will not see this elevation initial of pressure, but modulus calculation would be significantly simpler. In case when we need to see this initial behavior of pressure on the body, we will need to calculate and let's say better numerically simulate flow with viscous model. Please do not forget, you can always ask questions when they appear. Today I can see chat, so if you type inside chat, would be nice. Figure 5 is showing to us a typical re-entry body. This re-entry body is some space object coming back from space. For example, after some launch experiment in space, the re-entry vehicle must return back and bring results of experiment. Typical shape is shown on figure 5. We know that it should be planar, or let's say this shape which would create bow structure, bow shape, bow shock wave structure. This shape cannot have, for example, conical surface. If we have a conical object re-entering with hypersonic velocity in a very short time, this re-entry body will be totally burnt. Why? Because probably you remember from aerodynamics, energy is distributed in a different way. Energy is distributed in heating of body and heating of air. In case of figure 5, body is heated less and air is heated more. You can see that temperature is approximately 11,000 Kelvin. And in case of a conical body, we have a lot of energy that is transformed to temperature of a body, material by itself. So it becomes very hot, and any material cannot sustain 11,000 Kelvin. If body is heated until this temperature, it will disappear very, very soon, quickly. So this structure cannot fly at hypersonic velocity, cannot re-enter or go back from space at this velocity. Here also you can see that thermal energy is usually seen from two different sources: is the radioactive and convective heating. Heat rates and the relation between them is also shown on figure 6. We know that there is radiative and convective part. Depending on the value of velocity, relation between these two components is different. Unfortunately, these graphics we have in imperial units, but maybe in future we can transform it to C units. Also would be nice. The graphics would stay same, just values would change. On lower part of slide 7, we see chemical process or chemical reactions. They are reactions of decomposition, and they are reactions of ionization, dissociation and ionization of chemical species. Since most of re-entry processes which we must take into account happen in air, inside air, we have to see dissociation, recombination, or ionization of air and their components. First of all, dissociation of oxygen happens. That is taking place between 2000 and 4000 Kelvin. With respect to temperature, this dissociation velocity could be different. It can go in direction between oxygen molecules to atoms, and also can go back when temperature goes down. This atomic state of air can transform back. Our atomic state of air could transform back to molecular state. Same, but for higher temperature happens with nitrogen. Nitrogen at temperature starting from 4000 Kelvin approximately is transformed to atoms of nitrogen with heat consumption. This reaction is endothermic, so it consumes a lot of heat. And when temperature decreases, atomic state of nitrogen transforms back to molecular state of nitrogen, and the energy will be released. Same reactions, but for much significantly higher temperature, we can see for ionization when atom of nitrogen turns into ion of nitrogen with the release of electron, and the same happens with the oxygen. Turns to ion of oxygen with release of electron. Actually, probably you know that electron has a huge value of energy. It's a small but high value of energy. So transformation to ionized state or to plasma of gas is extremely energy energy. Sorry, I received another messages, and I need to turn off my cell phone. It's extremely heavy from an energetical point of view. It consumes a lot of energy on ionization, more than 9000 Kelvin. Also, we must remember that process of dissociation, recombination, or ionization are continuous processes. They happen at any temperature, even at our room temperature where we are right now. We have dissociation and we have ionization, but the rate of this process is very small. It's much more reverse velocity of process than straight process that in real life we do not see ions. Or let's say we see ions of nitrogen and oxygen and atoms of oxygen and nitrogen in extremely small quantities, You can say, okay, how much would be the rate? Could be rate 10 minus 12, 10 minus 16, more or less. So practically zero amount of atoms or ions of these species. But process happens always, and when with increase of temperature, this process goes more fast and transforms more and more energy and consumes more and more energy in this transformation. This is why we must take into account ionization and recombination and dissociation in any hypersonic flow. It's obligatory when you calculate hypersonic flow to include complete set of equations describing this process inside calculation of flow together with the flow equations. So we are solving two parts for hypersonic flow. Flow equations for non-isentropic transformation and chemical processes and ionization. So all these must be included inside the model of hypersonic flow. This is how, and this is why model of supersonic flow and hypersonic flow are different. Okay, model of hypersonic flow has has this chemical part. When I ask you what is different between hypersonic and supersonic flow, do not forget to tell that dissociation and recombination and ionization of gas may happen, and we must take into account these processes. How much it's different, we will see very soon in one example. You will see that consumption of these chemical process is around 80% of total energy, can be around 80% of total energy, so it's a huge difference. One example of application, there are a lot of examples nowadays, but just one of them is low-density supersonic decelerator developed by NASA for Mars landing. This project is not fresh, it has already many years, but since it has some experience, some results, we can find a lot of information, a lot of details. Is Mars decelerator, which uses theory of hypersonic flow in practical application to decelerate and to land on Mars with use of drag created by process of deceleration. So if we decelerate by drag, re-entry vehicle would be thin and a big size. Okay, let's say, yeah, big area, big cross-sectional area, which creates huge values of drag. What is different between atmosphere of Mars and Earth? You probably heard that Mars atmosphere is approximately 100 times less dense than Earth's atmosphere. So density is low. So to decelerate at Mars atmosphere area or area of the re-entry body should be significantly big. So this deceleration happens in several stages. First stage is more compact geometry at high hypersonic velocity. Then when velocity decreases, it opens some external or extra bumpers, let's say, which creates extra thrust or extra drag. And then when velocity is sufficiently small, it opens parachute. This parachute is huge, it's 33.5 meter parachute. Some land experiments, which you can find on NASA website, is the test devoted to validate structure. It's quite old. I think it has 5-6 years or more. And so there were several experiments about it, launched with balloon at high altitude, then propelled flight. Just a moment, let me change color. Propelled flight at higher altitude, around 60-70 kilometers, and then flight, test flight, cruise flight with a smaller parachute, right, and then descent, deceleration with big parachute, and return back to Earth. There are a lot of videos about this project in the internet. I actually usually showed this video on my classes, but I think since now we work not presentially, you can always find in the internet searching this LDSD project. Probably there are more very interesting videos. There are some photos taken from this experiment. Okay, this is ascent, and descent was it's not here. Manufacturing process, some photos of manufacturing process. I think it was a video. We just is now a picture. It's not a video anymore. And since test of such a body with the real launch on high altitude is extremely expensive. There are other ways of testing of such structure. For example, testing on test bench of NASA is a ground test. This accelerated with solid motors, achieving some velocities, high velocities, and measuring characteristics of flow, characteristics of drag created by this body. As you understand, numerical simulation is not enough. It must be, even for such important project or some such expensive project, must be proven by different type of experiments. One of these experiments is measurement of drag on the ground with acceleration. Another experiment is a test of parachute. It's a small scale. Sorry, I have error of notes application. Just a moment, I will launch again. Sometimes it crashes. Okay. Supposed to appear. Parachute in wind tunnel. You can see a huge wind tunnel in Air Force Ames Research Center. Huge, of course, it's a subsonic wind tunnel. You can see the size is 80 by 120 feet test section. To obtain meters, we, I think, must divide by 3. So it's almost 30 meters by 40 meters cross section of the wind tunnel. Very, very big size. You can put a complete airplane inside this test section. It's one of the biggest wind tunnels which exist nowadays. And this wind tunnel, of course, works with low velocity, low subsonic velocity. There is not amount of energy. It's not an energy unit which would allow to test this in supersonic or hypersonic velocity. Of course, it's low velocity wind tunnel. You can see people standing there, so wind is not so fast. Okay, wind tunnel creates some certain value of velocity with some good quality of velocity distribution known and perfectly controlled test conditions. So such experiment is extremely important. You can see visualization of flow with some smoke, and of course the parachute used for this test is similar parachute of a real mission, but it has small scale. Cannot put a 33-meter parachute in this wind tunnel. But small scale test is important. Even when we see this kind of experiment, we understand that creation of parachute or design of parachute is not such simple as one could imagine. It's a very complicated one, very complex task. We see that this parachute was tested inside the wind tunnel. Definitely this parachute was simulated. We can see this video on in the internet, and we can see that this parachute was tested on ground test and descent from 60 kilometers. So many tests before validation of such project. There are many projects devoted to hypersonic flow. You can find in internet nowadays. There are many military applications, hypersonic weapons, which probably each of you've heard about on recent days, and many countries nowadays have these developments because they bring technological advantage among many developments. Second part of our discussion today is the Newtonian theory. Newtonian theory is a quantitative approach to calculate hypersonic flow. Probably you remember what was the approach of Newton, which we studied at the beginning of aerodynamics. The approach of Newton was the following, that flow is going constantly until it reaches some object. So flow line is constant, right? And then when it reaches an object, it starts to move exactly with on the surface of this object. Of course, we know that it's totally wrong for subsonic and for supersonic flows, but this approach can be used for hypersonic flow because shock wave angle and the body angles are close one to another. So we can use similar approach calculating streamlines or direction flow properties in hypersonic flow. Of course, we know that Newton had no idea about existence of hypersonic flow or even supersonic flow. That is just by his name is given these equations. So with approach of theory, which is called Newtonian theory, we can analytically predict pressure coefficient. As you can see on the top left part of my screen, Cp would be proportional to sine square of theta, where theta is inclination of the body. This Cp is calculated for a flat plate. And since we can calculate Cp, we can integrate and obtain normal and axial components, normal and axial force, which you can also see on the screen that normal force would be infinite density multiplied by velocity in square by area and the sine in square of theta. It's a Newtonian approach. These formulas are not obtained directly from flow equations. These formulas are approximated parameters or approximate parameters, which allow us to have some idea about what are the forces in normal and axial direction of the flow which act on a flat plate. And with this reference, we can proceed in other calculations. For example, we can do numerical simulation and we can compare these reference forces with the simulation. We can see that in a simulation would be something close. Not equal, but close. Not equal because equations you can see on this screen are just approximations. They have no relation with the physical flow. Newtonian theory can be used not just for planar body, but also for curved body, as you may see on figure 9. There are two approaches, which is one is called Newtonian theory, classical one, and modified Newtonian theory for arbitrary bodies, where these two formulas are close, but as a reference for Newtonian theory is used coefficient 2. As a reference for modified Newtonian theory is used coefficient Cp max. This Cp max is a pressure coefficient which we might find on the stagnation point of arbitrary body shape. This modified Newtonian theory gives us better approximation of pressure coefficient distribution along the body. And theta and phi are changing with the coordinate, changing coordinate, right? Theta is a direction between tangential and velocity direction, and phi is perpendicular, let's say 90 degrees minus theta. Here is a comparison between Newtonian theory and simulation on cylinder. Okay, paraboloid. That paraboloid we saw on the previous slide. showing to us very nice correspondence between modified Newtonian theory and CFD simulation. This is why modified Newtonian theory can be used as a reference. This is a proof for many applications. We can use modified Newtonian theory as a base, just to understand how big, what would be the distribution of pressure mainly, and CP coefficient and forces. I think it's important because with the modified Newtonian theory, we can calculate by hand. We can calculate really fast, right? But we know that with finite difference calculation is CFD. It's a usually long process. Okay, sorry, Giovanna. Okay, no question, Giovanna.
No, sorry, it was a
Okay.
mistake.
No, that's fine. That's fine. I was thinking you wanted to ask a question. So next, a very small topic, results on a flat plate. You can see here Anderson presents to us a calculation how to obtain a lift coefficient, drag coefficient, and the lift to drag ratio for a flat plate. For this, we use modified Newtonian theory, or let's say Newtonian theory, pure Newtonian theory, because it's a simple body. Okay, just integrating. Advantage of this model is noticeable that lift and drag coefficient could be directly obtained from these formulas. Right, when we use approach presented on figure 12, where we have expansion wave and shock wave, equation system is more complex. You remember, right? We must calculate expansion wave, pressure on expansion wave, this transition. Okay, this pressure here, then we need to calculate shock wave. We must calculate this transition, pressure on the other side, and then calculating pressure difference and integrating along the plate, or multiplying pressure difference by projection of this plate on X or Y axis, we obtain the lift and drag forces and the lift and drag coefficients respectively. So we must use all theory we know for expansion wave, for shock wave, to calculate such flow structure if we don't know Newtonian theory. But if we do know Newtonian theory, calculation becomes extremely simple and extremely fast. Of course, would be a difference between result in equation 12 and equation 13. Would be a difference because theory of shock wave plus a theory of expansion wave is a result of analysis of flow equations. It's a solution of flow equations. But Newtonian theory is approximation, which is not solution of flow equations. So results between these two models will be different and will exist always. It's just for us to evaluate how much would be this difference. Closer we are to hypersonic flow, smaller would be the difference, for my opinion. I think we have such comparison here. No? So here, okay, is another part. Just a moment. Okay. Another part, lift to drag ratio for different angles of attack on a plate. Since we have function, lift, drag, and coefficients, and lift to drag ratio, we can plot this function just to see how different it is from real life and how different it can be for different angles of attack. We see that maximum drag coefficient possible to achieve is equal to, for flat plate 90 degrees rotated with respect to flow direction. Okay, is maximum. Then minimal one is 0 for 0 angle of attack. Since flow is not viscous, we can assume this. And also important here is lift to drag ratio. That theoretically lift to drag ratio can go to infinity to at a small angle of attack. right? Because lift would be going to 0 and much faster than drag. So lift to drag ratio goes to infinity. But for real applications, we have a point B, which you can see here, and this is giving us limited value of lift to drag ratio at some very small angle of attack. You can make, let me try to make a line. Okay, a straight line that is approximately, okay, at 5 degrees angle of attack, giving to us maximum possible lift to drag ratio with taking into account skin friction effect or presence of boundary layer. With presence of boundary layer, lift to drag ratio will never be infinite. It will be having at most a value a bit more than 6.3, 6.4, as we may see from these graphics. And please take into account this, that Newtonian theory is not always perfectly giving to us results, right? And especially for extreme values like 0 angle of attack. At 0 angle of attack, of course, there is no theory of Newton which would give us good result. Okay, at which point starts to be valid this theory of Newton? We can see by making one more line, and this is approximately 10 degrees. Starting from 10 degrees, Newtonian theory fits quite well with the real flow, where we take into account skin friction effect. Okay, accuracy considerations. These accuracy considerations show to us comparison between a wedge, cone, and Newtonian theory. 3. Wedge bidimensional case, as we already saw, is giving to us higher pressure coefficient and is not so close to Newtonian theory. Newtonian theory is better corresponding to flow around cone, around axisymmetric flows at high velocities. We see that at supersonic velocity, I will try to make more or less Mach 5 and make this line here. We see that here is hypersonic velocity starting. We see that, okay, is not so good correspondence between wedge and Newtonian theory, right? But between cone and Newtonian theory is already a very small difference. Already at Mach 12, 16, it becomes more visible that solution approaches, Newtonian solution approaches to real flow around cone and wedge. Of course, wedge is more distant from Newtonian theory and cone is closer to Newtonian theory. Analyzing flows and oblique shockwave theory, making infinite value of Mach number and transforming theta beta m relation, we can find that for hypersonic flow, there is a strict relation between beta and theta. That ratio between angle of shockwave and angle of body can be equal to gamma plus 1 divided by 2. This gamma plus 1 for air is how much? Is 1.4, 2.4 divided by 2 is 1.2. 1.2. So ratio between angle of beta and theta for air is 1.2, where we do not take into account change of gamma. We know that for hypersonic flow, gamma decreases. Once gamma will decrease and can be 1.2, 1.15, even for 1.2, this ratio will drop to 1.1. So angle of shock wave will be approximately 10% higher, from 10 to 20% higher than angle of the body. This is very important observation. Once you calculate hypersonic flow, we understand that between 10 and 20% extra you add to a body shape, and you start to receive shock wave. Shock wave will be between 10 and 20% of body thickness. Okay, then approximate calculation of pressure coefficient. This is some consequence for Newtonian theory. And one of the last questions is Mach number independence. What is Mach number independence? It says to us that for various bodies that work in hypersonic velocity, I will put here a limit of hypersonic velocity, Mach 5 approximately. It does not update. No, it updated. We observe constant behavior of drag coefficient for cone cylinder shape and for spherical shape. We see that for hypersonic velocity, drag coefficient stays constant. As a result, we can conclude that there is no, since there is no big difference in drag coefficient, we can perform experimental test on the limit of hypersonic flow, for example, at Mach 5. And we can extend all this data to any hypersonic flow reasonable, right? Until Mach 10, probably Mach 15. We can extend this data and assume that this drag coefficient would remain constant. From practical point of view, it means that we can provide relatively cheap experiment testing at Mach 5 and use these results of experiment for high hypersonic application, high Mach numbers. CFD is important. CFD works there, and along decades, CFD is the main method to study hypersonic flows. One of first applications were used on design of space shuttle, where we have simulated. It was very long time ago, probably 50, 60 years ago, started this project. And the computers that time were not so powerful, not so efficient, so you cannot see so many points on figure 18. Figure 18 shows to us calculation of pressure distribution for two different models. One model of perfect gas with gamma 1.4. It means that space shuttle flying in hypersonic conditions will utilize gas which is not changing with respect to temperature, and equilibrium gas which is changing due to dissociation, recombination, and ionization. As a result of this calculation, we can see that in many points, results are similar. For example, here, I think this is a part of the wing, right? But some part devoted to stagnation conditions, not stagnation conditions, I think it's, yeah. Some transition between wing and fuselage has significant difference between two models, as well as for the nose and as well for the tail. Where gradient of flow parameters change is high, we can see significant difference of flow properties. At the point where we have almost constant area, results of calculation using perfect gas model and equilibrium air model are very similar. Here we have the same task, but with the momentum coefficient calculated. You can see that there are two calculations of momentum coefficient, which is extremely important for control of flight vehicle. You can see that for equilibrium air and for perfect gas, behavior of momentum coefficient is similar, but the value is very different. for equilibrium air for a big range of angles of attack, it has positive value of momentum coefficient, and for perfect gas on very small region of angles of attack, it has positive and mostly negative values, and this shows us significance of use of equilibrium air in applications of hypersonic flow. It says that to calculate accurately and to calculate correctly global aerodynamic characteristics on re-entry vehicles is important to use a model of flow which takes into account transformation of gas with respect to temperature, like decomposition, dissociation, recombination, and ionization. So it's important. Nowadays, any calculation of hypersonic flow is performed with equilibrium air. Nowadays, there are no more simulations that use perfect gas as an appropriate model for CFD calculations in Mach number higher than 5. Even at UNB, when we have studies and when we perform some projects, especially TCC, our students use models of equilibrium air instead of perfect gas. Nowadays, nobody uses anymore perfect gas model for hypersonic applications. There are some list of additional topics which Anderson proposes to study devoted to hypersonic flow. We must understand that application of flow of high Mach number theory is quite important, quite wide. There are tens or hundreds of books devoted to calculation of hypersonic flows, theories of hypersonic flows, and there are several books in our library that describe such theories. I decided here not to give you all these mathematical models, but I would like to explain you that it's just top of the iceberg of huge complexity and the possible applications of hypersonic flow, which I tried to show you today. If some of you would be interested in future to work in this area, I will be happy to help you in this very interesting and important topic. This is the final slide of chapter 14. Quite fast, as I told you, we conclude today. Thank you for participation today, and have a nice evening, have a nice afternoon.